Dear friends, welcome to my channel. This is Open Channel Hydraulics, which is Chapter 2, Energy and Momentum Principles on Open Channel Flow. So my name is Johannes. So let us start with this topic, momentum equation. So we must follow this approach, which is very important. So in addition to continuity equation, in analyzing fluid flow situations, we have to check. So they are both derived from Newton's second law of motion. So in Newton's second law of motion, the net force acting on any fluid mass is equal to the mass times acceleration, mass of the fluid and the acceleration. So in this section, the force component will be treated on fluid particle in the direction of its motion. They are equated to the product of mass of the particle and acceleration along the streamline. So we have to just use Newton's second law of motion. So specific energy is actually constant for uniform flow. So specific energy is constant for uniform flow. So we will use this energy equation and can either decrease or increase in case of varied flow. So in case of varied flow, it will not decrease or increase. So in frictionless channel, total energy is constant and the specific energy varies. The specific energy will be constant if the channel is just to be horizontal. If the channel is horizontal, we will have a constant specific energy. Let us see. So you can see this diagram. So you have total energy at point 1, and at point 2 we have, so we have y1 and velocity at v1 square over 2g. Here also v2 square over 2g. Then frictionless bed you have. Then we have to see total energy is equal to at section 1 is equal to at section 2, and E1 again equal to E2 since it is horizontal and also frictionless, so these are equal. But if you have something inclined with some angle theta, but which is frictionless, then total energy may be equal. So this is total energy at this point equal to at this point, but specific energy will be different. So this is y2 and also v2 square over 2g, something higher than this one, due to the loss or due to the inclined position. You have total energy equal to total energy 2, but E1 is different from E2. E1 is different from E2. Let us see this one again. Let us see this one. So just we can see this one, which is very important. We can see just for some inclined position, since uniform flow, then you have total energy at section 1 equal to total energy at section 2, which is y plus v square over 2g. So since it is uniform flow, so you have the same depths, then E1 equal to E2, but total energy will vary. So total energy for uniform flow, since you have some inclination, so E2, ET1 will be larger than ET2. But for a drop, if you have drop, which is sudden abrupt in change in elevation, non-uniform flow, so T total energy at section 1 more than total energy at section 2. So this is, you can see total energy at section 1 and at section 2. Due to this abrupt drop in elevation, it will vary. So let us see now total energy and specific energy of the flow. So you have datum. So for this reference, datum Z1, Y1 and V1 square over 2G, which is alpha 1 energy correction factor. So you have total energy at this point and total energy at this point. So due to the drop in elevation, you have loss. So this is the loss or drop in elevation of the energy surface line. So this is the energy SF is the energy surface line, and this is the water surface slope. This is the energy slope, and this is the bed slope. So you have S naught, SW, SF. So this is water surface. Then at this point, due to the drop in elevation, it will just have some head loss. So At section 1, specific energy is equal to A1 Y1 plus alpha 1 V1 square over 2G. This is the total energy at section 1, and at this is specific energy, which is the depth plus kinetic head. But total energy, you have to add potential, which is this head. And the same is true for this one. You will have loss and also depth and potential head you have to consider. So I think with this, now once you have a drop in elevation, which is head loss at this point, total energy at this point will be, you have to add some loss. Then let us see specific energy, which is just the energy, the average energy per unit weight of water with respect to the channel bottom. So this is just the energy, which is the average energy per unit weight of water with respect to the channel bottom. So specific energy will be taken with respect to the channel bottom, but total head with respect to datum. With respect to datum, you have to include z elevation, which is elevation up to the bottom of the channel. So the piezometric head related to the bottom, which is z, equal to 0, which is water depth. Then, therefore, the specific energy is nothing, the sum of the water depth and the velocity head. So the sum of water depth y plus the velocity head will be the specific energy. So if the streamlines are straight and parallel, then you have to use this equation. So if the streamlines are straight and parallel, specific energy is the sum of water depth and the velocity head. So this is the specific energy. You have water depth, energy correction factor alpha, v square over 2g. Then you can just convert into discharge. So v is q over area. So substitute q over area here in place of v. In place of v, you substitute q over area. So q square over 2g a square. So this is the general equation for specific energy. So for a given section and constant discharge, the specific energy is a function of water depth only. Only the water depth. So let us see now. This is the graph showing the specific energy versus the depth. So if you have just potential energy and kinetic energy, this is the kinetic energy graph. This is the specific energy graph. Then for the same specific energy, you may have alternate depths, which is H2 and H1. Two depths may be given, H1 and H2, two alternate depths for the same specific energy. So if you go to this direction, you will have minimum specific energy, which is the critical specific energy. Then corresponding to this point will be HC. HC is the critical depth corresponding to the minimum specific energy. So you have kinetic energy graph and also specific energy graph and potential energy graph. So let us do the detail now. So if you have something, for example, if you have such graph, for example, let us see. For this E1, you have Y1 depth. For E1, you have Y1 depth, this depth. Then, since you have something E1, then E2, if you reduce the specific energy to this direction, you will just drop the elevation, which is water depth will be Y2. So if you decrease the specific energy, just you are decreasing again the water depth. Then if you go to this limit, which is to this point, you will get critical depth. So the level below this, which will be supercritical flow up to this point, and subcritical above this line. So we will have subcritical and supercritical. So supercritical and subcritical. So for this Q1, for example, Q1 is less than Q2. Then you will have just any calculation, we can calculate the depths of water corresponding to these graphs for the same specific energy, or you can vary this one. So YC will be 2/3 of specific energy. So or specific energy is 3/2 of YC. We will see this detail now. So this is a kinetic energy equation, which is Q square specific discharge square over 2GH square. So EP is just potential, which is potential energy due to the head, and this is the specific energy, which is H plus Q square over 2GH square. So this is a specific energy graph. Then total energy is nothing, potential plus kinetic energy, which is very important. Then we can just describe these equations with respect to any dimension we have. So point H and point G, you have for the same specific energy, you will have different depths as discussed previously. So for 45-degree angle, you have potential energy, which is the head, potential head. Then this is the specific energy curve, and this is the kinetic energy curve. So we can reduce or increase. Now let us see, when the depth of the flow is plotted against the specific energy for a given channel, section, and discharge, the specific energy will be drawn. So this is just a channel with irregular shape. So you have a strip of area with top dimension at the top surface. Then you have dy. So top is nothing, just you can have equation. Then finally you have this is critical. At critical state of flow, you have this graph with 45 inclination. Then you have any just discharge. So this is greater discharge. So if you increase the discharge to this direction, then you have just you have some equation for just greater than discharge from this one up to this one. Then we can calculate the depths of water corresponding to each discharge. So once we have this one, then finally we will just solve. So kinetic head is just V square over 2G. Then finally we have, so this is just for example, you can see Q1, which is the specific discharge at section 1, which is this one. Q1 is less than Q2, less than Q3. So we can have just this angle, which is 45-degree. So at this point, energy is equal to Y. Then you have critical and specific energy for this specific discharge, and for this one, you can calculate, but it is more than this one. So if you increase the specific discharge, you are increasing also the depth sometimes if discharge vary. So you can just demonstrate with this graph. So this is a kinetic energy curve, which is this one. So if you just increase, if you decrease the depth or the specific energy, then you have kinetic energy is increasing, and you have alternate depths for this point. 2 points, you can find alternate depths for the same specific energy, which is E. You can have E. Then you have 2 alternate depths. Then finally we have specific energy curve can be drawn. So specific energy curve and kinetic energy and also potential energy will be just calculated. So this is just the critical point, which is the critical depths at which the specific energy will be at critical. We will see the derivation. So let us see first critical state of flow. The critical state of flow is defined as the state of flow at which the specific energy is minimum. So to get minimum specific energy for a given discharge, or it is a condition for the Froude number equal to unity. So let us see. This is the general equation for specific energy. So Q is V over A. Then you can substitute just Q is sorry. This is Q is V is Q over area. Q over area. V is Q over area. Then if you substitute this one, Q square over A square. Then to get minimum specific energy, you have to differentiate. So dE with respect to dy is equal to 1 minus q square over ga square dA by dy. So you differentiate this equation, which is q square over ga q, then you have dA by dy. So dA by dy is top dimension or top water surface. Then once you have this equation, then hydraulic depth is area over top width. Hydraulic depth is area divided by top width. Then dE by dy is equal to 1 minus q square bs surface width over ga cube, then equal to, then you can substitute now. D is a over b, then you can have just a over b will be d. So q square over g a square, you can take 1a here, then a square times d. Then finally we get this equation. So this is a general equation. dE with respect to dy is equal to 1 minus b square a square over g a square d. Then you can just cancel a, then 1 minus b square over gd. Then you can have, just you can equate this one. Then finally, if you just divide by 2, then you have velocity head is equal to half of the hydraulic depth. So this is the criterion for critical flow, which states that at critical state of flow, the velocity head is equal to half of the hydraulic depth, So we have this equation, V over square root of GD is equal to 1 to make critical, or Q square T over GA cube is equal to 1. So which means full number equal to 1. This is the definition of critical flow. So just these 2 points already, we can just prove at this point. You have E1, then if you reduce the specific energy, you can get critical specific energy, which is critical depth. Then you have supercritical. This curve is up to this point. You have just supercritical. Above this one will be subcritical. So characteristics of critical flow. What are the characteristics? The specific energy and the specific force are minimum for the given discharge. For the given discharge, the specific energy and the specific force are minimum, and the Ford number is equal to 1. For a given specific energy, the discharge is maximum. The discharge is maximum at the critical flow. So we can just rearrange the equation dq by dy equal to 0, then differentiate, then finally we can arrive at the solution. So for a given specific energy, the discharge is maximum, but for a given discharge, the specific energy and the specific force are minimum, and the velocity head is equal to half of the hydraulic depth in a channel of small slope. If the slope is very small, the velocity of the flow in a channel of small slope with uniform velocity distribution is equal to the celerity of the small gravity waves, which is celerity is square root of gy. So just we can just see for shallow water, which is just shallow water caused by local disturbance, and the flow at critical state is unstable. So these are the main characteristics of critical flow. Then section factor Z for critical flow condition. What are just the section factor Z for critical flow condition? So the expression A square root of A over T, which is the hydraulic depth, is a function of the depth of water Y for a given channel geometry, and is known as the section factor Z. And V square over 2G is equal to D over T, which means Froude number equal to just V over G square root of GD equal to 1 for any channel, triangular or trapezoidal. You can use this equation, V over square root of GD is equal to 1. Thus, Z is equal to A square root of AD. A square root of AD. So, at the critical flow condition, Y will be Y critical, and ZC is equal to AC square root of AC divided by TC. Then you can just adjust again. You have this one, Q divided by square root of G. So at critical state, we can prove using this equation. We have V square over 2G is equal to D over 2 at critical state. Then you can substitute Z square over 2A square. Then finally, you have z square. Z square will be v square k square over g, which implies z is equal to velocity times area, velocity times area. Then finally, you have square root of g, then square both side, square root of both side, then q divided by g, which is the general equation for section factor, which is the square root of g. So this is the proof how you can arrive at q divided by square root of g, since you have v and d also we have. The section factor is already known, a square root of a over t. Then finally, we can just substitute, rearrange the equation. Then we have this equation, since d is hydraulic depth, which is a over t. Then by substitution we can find. So as a corollary, if z is the section factor for any depth of the flow, then q critical is equal to just square root of g times z. Z is outside the square root, and where QC, which is the critical discharge, represents the discharge that would make the depth Y critical, which is known as critical discharge. Critical discharge. So Froude number or regime of flow, the Froude number describes the different flow regimes in open channels. It is the ratio of kinetic to potential energy. So kinetic to potential energy is just the ratio of just kinetic to potential energy, which is the Froude number, and is used to characterize the open channel flow, whether it is critical, supercritical, or subcritical. So this is the general equation: V square root of G times A over T. A over T is the hydraulic depth. Then hydraulic depth is area of the channel divided by top dimension of the channel. So if Froude number is 1, it is critical flow. Otherwise, if it is less than 1, subcritical flow, or if it is more than 1, supercritical flow. So velocity of flow, V is velocity of flow, G is acceleration due to gravity, and D is hydraulic depth, and T is top width of the channel. So I think calculation of critical depth, critical velocity, and critical slope will be just, you can use this equation for rectangular channel. YC is equal to Q square over G the whole 1/3, because we know already just Q square at critical state of flow, Q square T over G AQ, G AQ, G AQ equal to 1. So this is the general equation for critical state of flow, or you can follow with the hydraulic depth, V square over 2G is equal to D over 2. Then if you substitute, then finally you will have this equation. So if you have T, top width of the rectangular channel is B, then finally you can have area, then rearrange the equation, take out Y. So Y will be the specific discharge square over G the whole 1/3. So this is a critical depth, or you can use Q square over GB square the whole 1/3. Then specific energy critical will be 3 over 2 YC. You will substitute in specific energy equation. Then finally, you arrive at this critical specific energy. For triangular channel, the same approach we will substitute in this equation. Then YC will be 2Q square over GM square the whole 1/5. Or critical specific energy will be 5 over 4 of YC. This is for triangular channel. For trapezoidal channel, again, for iteration, you can use this equation for trapezoidal channel. The same approach you will follow. Q square M cube over GB, the power of 5 is equal to 1 plus AC, which is eta C, the whole cube, eta C, the power of 3 over 1 plus 2 eta C, where eta C is given by this equation, MYC over P, where M is the side slope of the trapezoidal section. And if you need to use table data, you have just eta C with respect to M, and listen, you can find, just you can read this side. So Q M 3 over 2 square root of G B the power of 5 over 2, then this equal to 1 plus eta C the whole 3 over 2, eta C 3 over 2, 1 plus 2 eta C the whole half. So you can use this equation for table. If you need to use table, read psi with respect to m, then finally you can compute eta c, then finally you have crisscross here. Then finally you get YC. So I have other examples we will see. And the specific energy, if you substitute YC plus Q square over 2GA square, then this will be the general equation for calculation of critical specific energy for trapezoidal channel once you determine eta C. And for circular channel, a channel circular channel may be full or partially full. Then you have just to draw a line which is just subtended by this one. So this is the angle which is subtended by the outer surface. Sometimes it could be above this, then you will draw. Then for iteration method, we will use this one. Q square over G is equal to A cube over T. So top width of the circular channel is D sine theta. Then theta critical can be found if Q is given, then diameter is given, then you can find at what angle, which is theta. This is 2 theta. Then you can just bisect this one. Then finally, you can solve. To use table, just calculate Q over root of G, D is the power of 5 over 2. Then this is section factor divided by D, the power of 5 over 2, which is function of Y over D. Then finally, you can just calculate. You can calculate this one. So subtended angle, which is 2 theta, 2 cos inverse of 1 minus 2y over d is equal to f of yd. So these are just circular angle. And then area of the flow, you have d square over 8, 2 theta minus sine 2 theta. Then top width again, you can have t equal to d sine theta, p is equal to d theta, hydraulic radius is equal to this equation, which is d over 4, 1 minus sine theta over theta. So these are just for the circular channel. You can just calculate critical depths with table or iteration. So critical velocity, you can just calculate critical velocity. The general expression for just for calculation of fluid number, we know this equation, which is Fn square Q square T over Ga cube, which is for rectangular, which is T. Then use it to determine the state of the flow, which is critical state of condition. You can use V square over GD or square both sides, then square root V over square root of GD as in the previous slide. You can use this one. So critical velocity will be the general, just for general cross section, you can have this equation, square root of G times D, where D is area divided by top dimension of the channel. So velocity head at critical condition, this is the velocity head at critical condition. So in wide or rectangular section, D is equal to 1. Then we use for rectangular channel, we have G square root of YC. Otherwise, for any channel, you can use this equation. Okay, critical slope is just this one. Is the bed slope of the channel producing critical conditions. Just it depends upon the discharge, channel geometry, resistance, roughness, etc. So critical slope is the bed slope of the channel producing critical conditions. So for Chasey equation, you can apply critical velocity using this equation, which is VC is equal to C, Chasey roughness coefficient, square root of hydraulic radius times critical slope. Then you can calculate critical slope, which is this equation, critical slope using Chasey. If Chasey coefficient is given from Manning equation, you can use this one, SC V square N square R to the power of 4 over 3. So you have critical velocity. Once you compute this critical velocity, then finally you will just calculate critical slope. For direct solution, if discharge is given, you can apply this one. Otherwise, using English unit, you can have v square n square, which is this is critical velocity again, then 2.22 r to the power of 4 over 3. So I think with this, I think everything is clear. Maybe let me show you how we can use table. How can we use table? for trapezoidal section, and for trapezoidal section, once you compute just psi, which is z over d to the power of 2.5, then you read just from here, you read this one, you read this, then finally you can have y over d, y over d. So once you compute z over d to the power of 2.5, then you will have y over d. So this is for critical flow, and this is for normal depth calculation. You can apply this column. So for trapezoidal section, you have this for circular section. For trapezoidal section, yeah, this is for trapezoidal section. You compute psi first. Compute psi. Compute psi. Then once you compute psi, you have eta c. From this column, you can have eta c. So for every psi, which is given in the previous PowerPoint, which is, let me go back. For trapezoidal section, you compute psi. This is psi qm3 over 2 square root of g b to the power of 5 over 2. If you have this one, then you can read from table psi. Then eta c will be computed. Then from this, you can have yc will be computed. Otherwise, for iteration, you can apply this one. So you have two options, either table or iteration. So this is for circular channel, we can apply. So these are the tables for circular channel and trapezoidal channel. We will see more examples on this one, so that everything will be clear. So just critical slope, then you have just final solution for critical slope. Once you compute, then you will check with bed slope, etc. So you can see this is just as example, a trapezoidal channel with B 6 meter, M 1.5, conveys a flow of 17 meter cube per second. Estimate the critical depth of flow. Estimate the critical depth of the flow. So from critical state of flow, V square over 2G is equal to D over 2. Then we have section factor using this equation, Q over square root of G. So simply we can have this one. So the first step in solving this problem is to construct y versus section factor. Then finally, the value of the section factor is just then computed from the given data. So once you compute q over square root of g, which is equal to a cube over t, which is this one, then once you have this, then z over previous solution in the table will be read out from a table. So once you have the table, then from table you can compute other parameters. So I think we can compute other parameters. This is for circular channel and this is for trapezoidal channel. So psi would be computed. So psi is simple. This one. This is psi. This is psi, which is section factor divided by just this one, b to the power of 5 over 2. Then finally, we'll just calculate the result. Then once you have this, then you can compute. So I think this is just overall topic. Thanks for watching. Any question if you have? Thank you.